So my name is Adrien Schoen. I'm an intern at INRIA at the CIDRE Team, and I'm working on a research internship that I would like to continue in a PhD thesis, but that's another topic. And I would like to introduce you to my work and my current advance on this subject. So I'm working on realistic network traffic generation. So excuse me. So why do we want to generate traffic? We basically want to generate realistic traffic for in order to train detection system. So currently for training NIDS, we can use we can primarily use two methods, which is to capture real traffic on real networking device, but it's costly, it's often imbalanced, and because it's costly, the necessity to be updated is a severe drawback, because we have to redeploy every infrastructure to update the dataset with the new cyber attack. And another problem is on a real device, it can sometimes be anonymized if, for example, it's captured on a real network and not network devices for the experiment. So some real traffic datasets are anonymized, so it's another problem. And another way to train an NIDS is to capture traffic on a software-defined network. So this method inherits some drawbacks from the previous one. And another drawback of the SDN method, the SDN network generation, is that it's often unrealistic traffic at packet level, so the payload are often unrealistic. In the recent years, the state of art came up with a response which is to generate artificial traffic, so directly generating traffic using ML method. So we're not here implementing devices and making a connection between those devices. We're directly designing packets, crafting packets or flow with machine learning methods. So it's directly creating synthetic traffic. So first, would like to make quite a few statements of what do we call traffic, network traffic, because there is in the literature two different scales. So a traffic can be seen as on a flow scale. So we will here study communication between a sender and a receiver. This communication are constituted of multiple packets, and all of those packets share common information. So we can aggregate those common information to constitute a flow description, a flow level description of the communication. And there is the other scale, which is deeper, which is the packet scale. So here, the communication is seen as a sequence of bytes, directly a direct sequence of bytes exchanged between two devices. So what is important here, what we should bear in mind is that some information found in the packet scale is based on information at flow scale. For example, when we study a flow of the protocol TCP, for example, this information will be found at the packet scale. So some bytes of the packet scale, at the packet scale can be understood only if we have access to the flow scale, and the same for the other way around. So some information at the flow scale can be found all the information at the flow scale can be found at the packet scale. So that's the two scale of traffic, and we need to handle a bit both of them if we want to do a good generation. So the machine learning generation, is based on the fact that we train some models, some algorithms to learn repartition of information. But for this, in order to train those algorithms, we need some training data. And so for the training data, we here choose to use a dataset publicly available, made disposable by a university in Canada, the University of New Brunswick. And this dataset is composed of real capture so it's composed of pickup files of real traffic, and it's a dataset of 7 days of real traffic between 500 terminals. So it's composed of really huge pickup files. So for proof of concept, we during this internship we've only focused on a small part of the Benin traffic. We only focused on the Benin traffic, and during 1 day of traffic. So now that we have data, we can choose model to generate traffic. So I will first talk about how in machine learning generally we generate data. So I will here talk about what is mostly studied in generative machine learning, which is image, so image generation. So first method algorithm models that I want to introduce is the autoencoder model. So an autoencoder is a model that we train. We train this model to reconstruct the output to be as close as possible from the input. So it's composed of two parts. First, an encoder that represents the input inside a fixed length vector that we usually call the code. And the other part takes the code and transform it to an output, the same shape of the input. And we train the network in order to have this output as close as possible from the input. This is the general autoencoder method. So we want to recreate output as close as possible to the input. But for this general autoencoder, we cannot create new data. We can only reproduce the training data. Because a first idea would be to just take the second part, give it a random code, and see whether we can reconstruct an output near the input we trained the model on. But it cannot work because we didn't learn the representation of the code. So when we give a random code to the decoder, it often results in gibberish data. So nothing we really learned here. So we need to do something to use autoencoder to generate new data, and not only to reproduce the training data as close as possible. So for this, the state-of-the-art introduced a variational link in autoencoder. So here, it's basically a bit the same. Instead of the fact that we have two code, we have two code, one for the average and one for the variance, and we forced the output not only to be as close as the as close to the input as possible, but we forced the output to be set in a Gaussian distribution. So whenever we pick a sample from the distribution defined by the code here that we trained on,
we can reconstruct an output really near the input that we train on. So when we use variational link autoencoder and we learn the distribution of the training data, we forced this distribution to be normal, so we can pick a sample into a normal distribution and generate new data. So we learn, with the variation autoencoder, we can create new data. So another method, so that was the part for autoencoder, and now another model, another kind of model, family of model that we use to generate data are generative adversary network. So here, it's composed of two models. First, there is a generator, which is supposed to turn a fixed length vector, fixed random vector into fake images. And there is a discriminator, which is trained to recognize between the fake images and the real images. And the loss of the discriminator is a part of the loss of the generator. So whenever this model begins really good at recognizing fake images among real images drawn from the dataset, the generator keeps improving until it generates really good fake images that can fool the discriminator. So the training is both models are trained conjointly, and this is why it's called adversarial training. And we train both of those models up to an equilibrium point where they no longer converge. So I've talked about generation of new data in general. It was mostly with images. So our first idea to generate new network trafficking data was to encode the packet inside on an images. So we deal as the packet as a sequence of bytes, and we encode each of those bytes into 8 pixels in order to get a square image from a packet. So if the packet wasn't long enough or was too long, we cut it or we pad it with 0. And so we get a fixed image for each packet. So we can use methods that I've talked about to generate image that we will after transform back into packets. So we try this method with VAE and GAN, but it wasn't really good. It wasn't really really good. As you can see here, it was a reconstructed packet, so shown in Wireshark, and Wireshark didn't know how to recognize the packet and say that it was a malformed packet. So it was this encoding method and this way of generating network data by using image encoding wasn't really convincing during the internship. So why there is other reasons why it was supposed to fail, this straightforward method of encoding directly the packet to an images, is because first we decide to learn on all the packets of the dataset, but in fact, in reality, in a byte can have different meaning according to in a packet, a byte can have different meaning depending on like the protocol or so we cannot train a model to it's more difficult to train a model that can generate every packet. So we decide to firstly focus on the UDP packet because those are the simpler to generate and to handle. So Another problem here that can be easily solved is that not every byte of the packet needs to be generated. There are many fields in the packet that we can determine either by asking to a user or to just determine it by a flow features characteristic. And so by processing in our study in two scale, in a flow scale and in a packet level and at the packet level, we can suppress many bytes from the packet from the sequence generation, because those bytes will be determined at a flow level. So this is part of the global scheme here that I present you. So here we will act at two levels, not directly straightforwardly encode a packet into an image and asking our model to generate this image. We will try to split the work in order to do it more fluently. So first, there are some information that we can ask about the user, or that are not dependent, so that we can ask to the user. So this will be the addresses and the protocol. So we ask the user what address, what protocol do you want to generate a flow of, and with this input, we generate a flow characteristic, so characteristic of the flow that we want to generate. So it can be a duration of the flow, number of bytes, number of packets, number of TCP flags in the flow. So we use a specific model to generate those characteristics, and from those characteristics, we can generate the set of packets, because in the payload, in the packet, many of the bytes, many of the fields will be directly determined by those features. So if we previously we were directly trying to predict to generate the set of packets without generating some features, and it was really way much harder than this method. So we are trying. We've done the first part for the UDP flow, because we're focused on UDP now, and so so the first part was to generate flow characteristics, and all the flow characteristics in UDP are contained in the headers of the packet. Okay. So this we reduced those characteristics to 6, which is the time to live of the packet of the flow, the source port, the destination port, the duration, the bytes, and the number of packets in the flow. So the number of bytes in the flow and the number of packets in the flow. So so as I said, our model for flow characteristic generation, which is the same as header generation, because all the flow characteristic features in UDP are contained in the headers of the UDP, is that we first ask the user for some information like addresses. We then use our header model to generate our header, and when we have the header, we can use a payload model to generate the payload and reconstruct the packet by concatenating the header with the payload by concatenating. Yeah. So the first part, so generating a flow characteristic. So as I said, we focus on 6 characteristics for the flow. So the flow feature. So we first collect the flow features of our dataset, and we focus only on IPv4 very short flows for first time. So that only contain 2 packets. So all the dataset here is just, yeah, it's UDP, it's DNS packets, DNS flow that contains only 2 packets basically. And what's important here is that for the generation and for training the model, we transform numerical value into their binary representation, because here you see, for example, the port destination is represented by a numerical value, but actually it's discrete features. So we would like to work with discrete features, but the generative model doesn't work with discrete features. So we can either do an embedding or going straight through with binary transforming the numerical representation into a binary vector, and we use this binary representation to do so. We will transform this value into binary and learn the analysis. So how is it going? So we train basic model to generate those 6 features with our training dataset, and to evaluate those models, I drew here for each value the distribution of for each feature, the distribution of the value. So there is in blue the distribution of for the training dataset, and for red the distribution for the generated data of our model. So we can see here, for example, that, as I said, there were only a flow of 2 packets. So there is only, like, it's a Dirac centered around 2. So there is only a flow with 2 packets. So, and the models, okay, in red recognize that, so it's well superposed with the blue distribution. The same for the time to live. So there were only 3 values in the dataset, and it's mostly 3 values also in the generated, even if we have some problem here. The same for the ports, and for the duration, we can see that, yes, the curve of the generated data follow well the curve of the real data. So we have also other metrics of comparison. We used Shannon-Jensen and more conventional metrics to evaluate our model. And yeah, it's way more good than the first one. For example, this is a packet generated through this method. So we first give the source, the MAC address and the IP address to the model, and it gives us a really well built packet. So it directly recognizes that even if we didn't give him payload, it's recognized directly that it was a DNS packet thanks to the port information. So it was really well with SCAPI. So here it's 000 because I didn't tackle the payload generation yet, but that's what we are going to see now. So now we can generate headers quite well, and so we would like to tackle to the header generation, not having just 0 here, and so we need to generate the UDP payloads. So instead here of dealing with image as we've done previously, we directly deals with the payload as a sequence of bytes, and so it's like a sentence of words. Instead of the sentence, we have the payload, and the words are the set of bytes. So we will use a method already used in natural language processing to generate the payload. So for example, here we have RNN. So it takes 1 token at a time to generate the other. So it began with the start, and it began with the to go through the model to generate the next word, and it will give the previous word and the previous states to generate the other one, and at the end generate the sequence. So our UDP payload. How do we encode our UDP payload? First, we take the packet, the UDP packet, we discard the header because we tackle with the headers generation previously. We just keep the payload. We tokenize it, which means we transform the payload into a sequence of smaller parts. So that's where we can use bgram or other parts. And we train a language model to understand the relationship between those tokens. So in a sentence, words have relationship among them. There is verb, there is subject, and so to understand those relationships, we need to train a language model, and so we will do the same with our sequence of bytes. And when we have our language model, we can sample from that model. So there is a lot of different techniques to sample the model. So to sample a sentence from that model. And when we have the sample of that sentence, we can evaluate the sampling through an actor critic method, such as GAN, for example, as we were already used to. So where I am now, so I'm currently learning about language model, how to use them, what are the different kinds of language model, and how, most importantly, how to train them. I plan to first use them for UDP payload generation, so the payload of the UDP packets. And after that, I will be able to reconstruct all the packets in a flow. But I would like to study the time and byte repartition of packets inside an UDP flow, because all the packets in a UDP flow don't have the same size, for example. So this information, I would like I will have to learn it on another part because it's completely independent from the two from the two previous generation. And after that, I will try to tackle TCP generation. So it's a bit harder because there is a three-way handshake. And so I will try to tackle with this. And after that, either integrate our model inside an API to simplify the usage, or either trying to deal with encrypted payload, because for the moment we didn't use encrypted payload. So thank you for your listening. Don't hesitate to ask questions.